So, I would like to introduce you Professor Jian from Syracuse University. She's very kind of her to be here with us today to give us two short mini courses about management of data, research data. So, thank you very much, Professor Jian. Uh, it's an honor for us.
Obrigado. uh, so good afternoon, good evening. You know, it's the transition time. All right. So I know it's been a long day already, and you may feel tired. So if you doze off, and that's okay. I don't mind. Uh, but I hope the content will be interesting enough for you to stay awake. Um, so after I think after the presentation, you should looking have the big dinner to look forward to. So that's something very. It's always good to have something look forward to, right? All right. So this evening I have two presentations, and the two are related. The first one, oh, the first one is to it is about educating new breed of data scientists for research data management. As I mentioned yesterday, my research and practice area is mainly surrounding the research, academic research, not in the business world. Although I do have colleagues who uh, conduct research in the business world, but that's not my strong area. So in this presentation, I will be talking about the data science in more details, and also the data scientists in the context of research data. And then I'll give you some introduction about the data science curriculum in our school, and how it evolves into the current shape. And then I also are going to share some lessons learned from my project, and then we'll talk about what's the current status of our certificate, advanced certificate. I'm sorry, certificate for advanced study in data science. That's the program. Anyway, so put our, as I talked yesterday, and the big data, and not just in the business world, it happens in almost all aspects of our life. In especially in the library information science field. This image I took from I think I took from this read write, and this is source, and it talks about big data and Library of Congress, and have all these like 147 million assets. Assets, if you consider each book, each digital object as a digital asset, and that's also considered as a data. So just way off a little bit. In our school, I teach a course called Foundations of Digital Data. And the digital data in this course that I define broadly as all digital objects, not only in the numerical format, but also images, videos, and those digital models, and a lot of things. And later you will see what are these digital data encompass, and it's really amazing. And the very daunting today. So we're feeling the pressure, and so these big data exists not only in our healthcare, and the image you are seeing, this black background, is actually the brain scans brain scan images, and this is the other one is the DNA sequence, healthcare, and then in our neighborhood, if you look at the map, and you can see overlay of digital data on the map, neighborhoods and hotels and, historical sites and all that different data are overlaid on the map. So this is our neighborhood, and you can see the development of the landscape and, the distribution of houses and resident and business buildings and etc. And in the business world, that's even more complicated and large variety. So you have like vertical apps, various applications, various digital data services. Like I constantly receive like cloud data storage, commercials, as well as just today I received another contact selling me Hadoop, storage capability and parallel computing capability. So all those are happening. And in science research, and just a couple of years ago, the Science magazine published a special issue on scientific data. They talk about the data deluge and how we can competently address the issues brought about by this data deluge. Okay, so there, if and in order to understand the research data, we will I think it's helpful to understand how science research has evolved over the years. And if you talk about the science paradigms, and 1,000 years ago, it's basically science was empirical, basically observing things. Remember Darwin's and even before him. So those are the describing natural phenomenon. So if you fast forward to a few hundred years ago, the theoretical research began to branch out using models, generalizations, and then you move to a few decades ago, and there's a computational approach, simulation, complex phenomena have been studied because the tools expansion and development in, greatly increased researchers' ability to deal with large-scale data, to collect large-scale data, and use large-scale data to solve large-scale problems in our society, in our natural environment. And today, the data exploration is also called e-science. It's unifying the theory, experiment, and the simulation. And along this process, there are data captured by instruments like I described yesterday, or generated by simulators, and processed by software and information knowledge stored in computer. So there's all these data analysis tools, and all these now come together and form what we many people call e-science. And there, in terms of data size, we know the smallest is byte, right? And then we have kilobyte, megabyte, gigabyte, terabyte, petabyte, exa, zeta. So if you look at these increase, it's really amazing how fast the data increase has become in the recent history. So the research data collection, as I just I think I repeat this slide I used yesterday. I'm not going to give a detailed explanation, but from this slide, you can tell that you know, there are different sizes. Data collections, there are different sizes. There are different you know, levels of management. There are also different you know, varied quality in description and the representation. So among all these, you know, the large massive amount of data and large large quantity of tools, formats, and all these, the new concepts keep emerging, such as e-science and big data and data science. And you hear these terms very often these days, a lot of them. And the wordy, you know, from the tools, you using the wordy tool, you can see these key terms like digital e-research and interdisciplinary data, smart data, algorithm. All these words and these concepts, although they are not new, but the you know the what's new in all these is that when you deal with a large data collection or data set, you are requiring to use many of these things all together. You are no longer just dealing with one aspect. For example, in the old times, when you do social sciences research, say you have conducted a survey, you collected, you know, some survey data, and what you need to do is probably just you know, SPSS to code the data and then crunch some statistic results and do some tests, and that's about it. But these days, even for surveys, you know, if you have large, you know, large scale survey, and the simple, if you want to conduct some more sophisticated study like machine learning or some other machine learning data mining kind of analysis, it's no longer enough to just use SPSS or just use SAS, because these days the data you generated, the users and are no longer just researchers, and the users can be anyone, average citizen, the general public, the policymakers, and the decision makers, and researchers, students, learners, and all the people. So, for example, there's a trend in the US now called citizen science. The citizen science, one of the kind of citizen science is you know, keeping a tab on the water resource, the quality of the water resource. So how do you do this? Because there are so many lakes and rivers and, you know, streams. It's hard for the researchers to cover every lake, every stream, you know, everywhere. So what they do is they devise some apps. So if you know, the average citizen or tourist, you go somewhere, you discover some you know, some problems, and then you can report. For example, the, you know, some say a company poured some you know, polluted water into the lake, into some, and then you can report that. And also the other, I think one of other citizen science famous citizen science project is called eBird. It's conducted in Cornell. I don't know if you ever if you have heard about it, but it's very good project. And eBird is basically the birders. Those, you know, there are many people who are bird lovers, and they just go on the tour, go to the mountains, and, you know, use their binocular watching birds. And whenever they discover some new species and some, or not necessarily new species, something, they can report through the eBirds interface to record the data, like say time when they observed this type of bird, and then etc. So when you have all this data reported from all over the country, and now because it's on the web, people from all over the world can report the birds, like say migration and the number of particular bird type of birds, and to that system, and the system run algorithms to generalize patterns, to discover useful scientific findings. And this is really something that we have never thought about in the past. So this is all about big data, and the big data can be collected by all of us, average citizens. So that's what's new about this data science, big data, or e-science. It's because it's no longer just you need single tool or a single method. It's all of it. It's all of it. That brings up some new challenge for the library information science education. What these challenges are. So let's look at some job descriptions from in the scientific data management field. This is the scientific data management specialist. So if you look at the words that have been highlighted, design, develop, implement, and manage. So this is the basic skills, and develop and improve infrastructure supporting the system, and interface. You need to know something about interface and clarify. So that's another. And then there's also administer, assure, interact, track, collaborate, assist, test, and create and maintain. So all these responsibilities, although not new, but the things they work with, it's no longer just traditional. Um, and this is another data modeling management specialist. Work closely with the high performance computing and the IT manager, develop and design and organize and integrate and manage. So you see all these verbs are the skills you can from because I'm an educator of information professionals. I tend to think, oh yeah, when students graduate from my school, from our program, we would hope our students at least have some basic skills and knowledge in order to perform these actions. So that's essential. So now, if we turn to look at the marketplace, and the marketplace demand for data science skills, this is a survey done by IDG Enterprise. So if you look at this, the top one, I can, okay, let me read. Perhaps many of you can see them clearly. So the first one is database programmer. And second one is business analyst. Third one is data analyst. And then this one is engineer and data architect, a research analyst, director or manager of analytics. So a lot of data analytics analyze, and data related and research related. So you see all these job market, demands requires skills in management, in data, and in analytics and research skills. So there's this is some kind of very very informing trends in the job market. So when we look at all these what's happening in research, what's happening in the IT world, as well as the information world, data world. And then you see all these. It's no wonder that people invent this data science word to encompass all the things that's required in order to work with these new data scale of data, and new being able to address problems that we would have been unable to address with our limited tools and data, previously. So data science, what is it? And what does it mean for future information science workforce education and employment? And this is the question that we as educator for future information professionals need to address. So I think that was back in the back about 5 years or so, and we were trying to think about a way in order to produce the kind of graduate students needed by the market, and so that's the kind of question we asked at the time. So what is data science? Yesterday, I cited this definition from our Associate Dean for Research, Jeff Stanton. In his book, by the way, his book, Introduction to Data Science, is free for download. So if you go to our school's website, go to the faculty directory, find his name, Jeff Stanton, and there's a link to his website. And then the book downloading link is on his website. You can download the free book, Introduction to Data Science. It's a very popular book, and it's free. So, so once we define what is data science, then the next question we need to address is why data science? Why do we need data science? Why we work in this area? We want to create something. So based on our experience, I think we have 3 reasons to address why data science. One is, right now, the available data on a scale, on a scale of millions of times larger than 20 years ago. So it's no longer just small, a few spreadsheets and that's all about it. But it's like whole database, and the database is no trivial. It's millions of rows of data, and how do you deal with that kinds of data? So that's because the data has the massive amount of data is requires new ways to address these issues. And these data are heterogeneous. They are not homogeneous. They are not consistent in format. They are not consistent in content. They are all over the place. So they are with different representations. And as I showed you earlier, some examples. So they are also located in distributed systems. And these systems are built with different platforms, different language, different system software. So they are all different. And how do you work with large data when you need to take data sources from different places, different systems, in different formats? And how do you work with this data? So that requires a systematic solution to deal with these problems. And finally, in the chaotic information life cycle, where there's a little time and effort is spent on what should be kept. So there's a lot of these issues. Just give you an example. One of the reasons we always, I think, always hear from interviews, from conversations with researchers, is that I can't spend time on data management. I I don't have time to manage my data, because if I spend time to work on data management, I won't have time to spend on science. And it's the science that counts, because if I don't publish, I don't get project done, then I'll be in trouble. So there's no motivation, no incentive for people to manage data. So that's why, in the end, you get chaotic data all over. So it's not uncommon for a scientist who had done a great project, and all the data were, data analysis, data collections, data processing, have been done by his or her graduate students. And once the graduate students graduate, then the professor has no idea. Sometimes the data is lost. Sometimes, it's hard to get hold of those data, even though he may still have the files, but it's difficult to know which is which. So it's a chaotic situation in many faculties' research projects. And of course, there's always the technical issue, diverse and legacy infrastructure, mainframe running cobble connected. So there's a very ancient programming language, created data sets, and then today there's only particular machine, particular software that can read the data. So this is kind of a data preservation, long-term access issues. So data science are trying to address all these data, so all these problems, the data life cycle that I described yesterday. So when we collect the data, we process the data, we analyze the data, and we put data in archive. But over time, the software used to read the data will become outdated, and the newer computers will not have the kind of software you used to collect the data, process the data anymore. So if you don't have that data preservation policy strategy, and then you will be, in big trouble. And I think there are some hard lessons learned from U.S. federal agencies. I think a popular story was that during the 60s, there were some, I think, remote sensing, those done by NASA, and they accumulated large collection of boxes of magnetic tapes, and those data are stored in those magnetic tapes, and the magnetic tapes are stored in boxes, carbon boxes, and over time, those boxes have been moved around from one location to another. But after several moves, and nobody knows where this box went. So then, fast forward the time to the 1990s, and someone remembered those, remote sensing data, and wants to compare how the climate change, global warming has affected, say, the Antarctic ice, ice cover, or the glaciers, shrinked, or the snow caps on certain mountains has raised to new height. But excuse me. But when you don't have that, the data from, like, say, 40, 50 years ago, and you don't have a comparison, you don't know what today's data explains. So that kind of data lost is lost. So I don't. I think in the end, excuse me. In the end, someone did locate those boxes, but once they located the boxes, I have water. Once they located the boxes and they discover they don't have the software and the hardware to read the data because those tapes are ancient. So the data preservation issue is no trivial, especially if you want to preserve the data that can only that occurred only one time, once in the lifetime, like volcano eruptions, earthquakes, and all those natural data situation. So that says a lot about why data science. Okay, so whoops. So the data science and the research, if you, I think, as I mentioned yesterday, the data life cycle and the research life cycle has some overlap. So they are, closely intertwined together. And on the one side, you need to think about how to plan, design, and consult for, implement, and evaluate data management projects and the services. That's one side. So this side is not necessarily all, programming, technical coding, not all that, but it's many of them are, I consider, as software, soft skills. Because when you think about the ability to be able to, generalize and, survey a domain, generalize the key entities, key concepts, and the key relationships, and turn the concepts, relationships into some kind of conceptual model, and then use this model to design some system that can meet the user needs, for discovery, for use, for management, for internal use, for external use. And this is not simple task, and the skills, and especially that conceptual modeling skills is very difficult to learn through through a short course. It takes experience, takes practices, to develop. That's But on the other hand, if you think about the technical side of the data life cycle, research life cycle, there's you need to think about how to ingest data, store data, organize data, merge, filter, and transform data, and create analysis ready data. So the analysis ready data, that's something very important and very, it's kind of new in terms of this data science stuff. So the on the one side, you have to have this planning management kind of mind, on your right brain side. On the other side of your brain, you also need to think about the actual operation cycle. So that's data science and the research. And I'm quoting another researcher's definition about data scientists. I think Thomas Davenport is a famous, I think it's a famous researcher at Harvard. He defines that data scientists are the people who understand how to fish out answers to important business questions for today's tsunami of unstructured information. I think this is well described what the task is. But how are we going to get there? How we are going to be able to do this? So I'm using this this is a slide from Jeff Stanton. He did a project, I think a few years ago, and he and his co-author developed this diagram. In the center, you see the data scientists and the kind of skills that we expect data scientists to have. For example, information analysis, and then information visualization, organization and visualization, and solution integration, and data curation. So these 4 big areas, in fact, can be expanded to more specific. So if you talk about information analysis, is mainly expected of domain experts. So you have expertise in a specific